Every token sent to a large language model incurs a latency and financial penalty. When building persistent AI agents, pushing a user's entire conversation history into the active context window quickly overflows the model's limits. This table compares context costs during an agent's reasoning and acting cycle. Without tool calls, cost is baseline. One tool call doubles the input cost because the model must reread the entire context. Two sequential tool calls triple the cost. Standard retrieval augmented generation attempts to mitigate this by storing raw text in flat vector databases. However, basic semantic search retrieves disconnected snippets without understanding the temporal or relational weight of those facts. Relying strictly on flat semantic search forces the agent to constantly page in heavy, disorganized tool calls. The context window inflates, latency spikes, and the illusion of continuity breaks. To solve this, we map our architecture to the Cognitive Architectures for Language Agents, or KOALA blueprint. KOALA establishes a strict boundary between working memory, the active context for the current decision cycle, and long-term memory, which holds persistent data structures across sessions. We engineer this boundary using a 4-tier compressive memory stack. Raw episodic data enters level 0, extracting to level 1 semantic facts, inferring level 2 insights, and synthesizing into a level 3 block. Here, systems aggressively filter the data, decreasing text volume while increasing structural density. Progressive compression allows the system to distill an infinitely expanding relationship history down to a cheap, reliable payload. Level 0 episodic memory serves as the ground truth. These are the unedited, raw JSON message strings of every conversation turn. Attempting to summarize these raw messages using fixed clock times, like morning, afternoon, and evening windows, arbitrarily cuts conversations in half across time zones and irregular schedules. Instead, the architecture uses a stale session scanner. It monitors the database and triggers only when a user has been inactive for 15 minutes. When that natural activity gap occurs, the scanner groups the preceding messages into a burst narrative. Rather than constantly overwriting a single running summary, it locks an immutable record into place. Indexing memory around these activity gaps captures true semantic continuity. The resulting narratives align exactly with how the user actually communicates. Level 1 semantic memory extracts structured knowledge from those narratives. To enable dynamic recall, the system moves off flat vector lists and implements a graph relational model natively within PostgreSQL. The physical schema splits into nodes representing entities, like a person or city, and edges representing predicates. The PG vector embeddings reside directly on these connecting edges. The system writes epistemic humility metadata to every edge. It mathematically distinguishes between a fact the user explicitly stated and a conclusion the agent deduced. Background extraction workers evaluate the ambient emotional tone of raw messages, tagging extracted facts with an emotional identifier. During a similarity search, a fact tagged vulnerable or intimate receives a 0.15 algorithmic weight boost, prioritizing it in retrieval. The database evaluates what the user said, mathematically weighs how certain the agent is, and calculates the emotional weight of the moment it was shared. Level 2 analytical memory operates above the factual graph. It stores behavioral patterns, user personality traits, and the procedural goals the agent is pursuing. The processing for these L2 insights occurs completely offline. Scheduled nightly background workers analyze the accumulated graph data without adding latency to the live chat. Level 3 synthesized memory is the ultimate layer of compression, taking the form of a single document called the companion journal. Every night, the background workers take the sprawling network of L1 facts and L2 insights and distill them down into a dense 750-token text document written from the agent's perspective. Months of complex relational history are compiled into a highly efficient mental model that costs fractions of a cent to evaluate. The system enforces a hard architectural separation between real-time memory retrieval and offline memory writing. Before the reasoning agent even starts, an observer node budgets the context window. It preloads only the highly compressed L3 journal and the most recent L0 burst narratives. The heavier L1 facts and L2 analytical insights are deliberately excluded from the prompt. The agent must use specific tools to page that data into working memory only when the conversation demands it. On the right path, facts extracted by background workers are strictly gated behind a 95% confidence threshold. Anything lower is rejected to keep hallucinated logic out of the database. Enforcing strict read and write boundaries protects the live agent from catastrophic latency spikes, while entirely preventing real-time memory pollution. Because writing happens offline, the architecture utilizes system downtime to perform sleep processing, consolidating raw experiences into a deeper understanding. The mathematics governing how the system forgets are derived directly from the Ebbinghaus forgetting curve, a foundational concept in cognitive psychology. This chart tracks retrieval reinforced decay. Graph edges accessed via tools gain a 5% importance boost. Unused edges suffer a slow mathematical decay in confidence. When an unreinforced edge's confidence score drops below 0.5, the database flags the memory with a probing state. During the next cycle, the agent detects the probing flag and autonomously generates a natural check-in, reaching out to the user to verify if the stale information is still accurate. By pairing a graph relational pipeline with biological decay mathematics, the architecture operates as an active, self-correcting cognitive engine.